So the last thing we're going to talk about involving capacitors is what happens if you put them in series or parallel with one another. Let's look at parallel first. So here you can see that I've got two capacitors that are in parallel with one another, and the same voltage is being applied across both of them. Now, because it's the same voltage and the capacitor values could be different, therefore we know that the charges could be different as well. So I've labeled them as Q1 positive and negative and Q2 positive and negative. Now, if there's going to be an equivalent capacitance, the deal is that that equivalent capacitance should have the same amount of charge induced on its plates for a given voltage as this combination of two capacitors had for a given voltage. So if Q1 and Q2 were the total charges that were on those two capacitors, Q total should be Q1 plus Q2. So we need to remember that. That'll come up in the work we're about to do. We know that that the equation for relating charge to voltage is Q equals VC. So Q1 equals V times C1 and Q2 equals V times C2. We don't need to put subscripts on the V because the voltage is the same across both of them. We know that Q tot equals Q1 plus Q2. We just derived that. And I can substitute Q1 equals VC1 and Q2 equals VC2. I also know that the definition of capacitance is that it's going to be the charge divided by the voltage. So for this equivalent capacitor, it will induce a total charge Q tot and when a voltage V is applied across it. So C equivalent is defined to be Q tot divided by V. Well, we have an expression here for Q tot, VC1 plus VC2, and then that's going to be divided by V. So the V's are going to cancel. We're left with just C1 plus C2. So take a moment and consider when two capacitors are in parallel with one another, we can combine them by simply taking the sum of the two capacitances. Remember that that's the opposite of what we had to do for resistors. For resistors in series add by summing the two resistances, while capacitors in parallel add by summing the two capacitances. So in this case, we see that resistors and capacitors combine in the opposite way. Let's see if they also combine in the opposite way for two capacitors in series. Spoiler alert, they do. So we're gonna consider two capacitors in series. Let's look at this circuit diagram here. We can see that that we have two capacitors, C1 and C2, a total voltage of V being applied across the combination of them. And then if we combine them together into a single capacitor, that total voltage V will just be applied across C equivalent. So we know that it turns out that the charge on these two capacitors has to be equal to one another, because this bottom plate of the top capacitor and the top plate of the bottom capacitor are sort of an isolated island. If charge leaves one of these plates, it has to go on to the other plate, and vice versa. So electrons are going to leave this top plate of the bottom capacitor. They're going to go on to the bottom plate of the top capacitor. There's nowhere else for them to go. They can't jump across this barrier here. And so therefore we know that positive Q and negative Q have to appear on these two plates, and therefore we know that the two capacitors, plus Q and minus Q on the bottom, plus Q and minus Q on the top, those two charges have to be equal to one another. Now the voltages don't have to be the same, because if the capacitances are different and the charges are the same, then the voltages have to be different. So we have an equation here for V1 and an equation here for V2. Given the amount of charge that is the same on both capacitors, and then given that the capacitances could be different, the voltages can also be different. So we know that the total voltage across the equivalent capacitor has to just be the sum of the two voltages across the original two. So here you can see if we did Kirchhoff's voltage law, minus V plus V1 plus V2. So minus V plus V1 plus V2, we can move V over to the other side. So V equals V1 plus V2, and we have an expression up here for V1 and an expression for V2, and so therefore this is Q divided by C1 plus Q divided by C2. That's the total voltage. Well, we also know that by the definition, V over here has to be equal to Q divided by C equivalent. So that's the definition of capacitance in a way. So V equals Q divided by C equivalent, but from up here, V is also equal to Q divided by C1 plus Q divided by C2. So I can put that into equation 21 as well. So now you can see that if I sort of ignore the V part of this, I have an equation that says Q over C equivalent equals Q over C1 plus Q over C2. I can divide both sides of that equation by Q and get 1 over C equivalent equals 1 over C1 plus 1 over C2. And this is kind of the definition for how resistors in parallel add, but it's how capacitors in series add. We can then reduce that to say C equivalent is 1 over C1 plus 1 over C2. which for two capacitors can be reduced down to the product divided by the sum. C1 times C2 over C1 plus C2. And that's going to be our equation for how to combine two capacitors in series. Again, notice that this is the opposite of resistors. Resistors in parallel add by calculating the product divided by the sum, and capacitors in series add by calculating the product divided by the sum. So it's just a good rule of thumb. Once you remember how resistors add, just remember that capacitors are going to be the opposite. That if you have them, if capacitors are in parallel, then they're going to add by just summing the capacitances, and it can be more than two. It could be 3, 4, 5, however many. And that if you have two capacitors in series, they add like resistors in parallel, which if you have just two, you can use the product over the sum. If you have more than two, then you have to use the sum of the reciprocals is equal to the reciprocal. Or you could just combine two and then combine the third one in with it. So that's enough information for you to do the last sort of example problems for today, the series and parallel capacitors example problem. Once you've done that, then you're ready to come to class and do some in-class exercises.